That's a lot.
Hi everyone. We're going to pick up where we left off in chapter 9. So, to rehash here, as what we talked about yesterday, chapters 9, 10, and 11 are all calculus topics. Now this is like calculus light, in that we're skimming through quite a bit of depth and detail. We're just omitting in the interest of being able to do what the IB expects us to do. This chapter 9 will not have a test attached to it. I'm just going to give you guys a take-home quiz to do during the topics of chapter 9. That will probably be something I give you before heading into that conference. That'll be your virtual conference day assignment. We'll just be work on that. Feels pretty easy. And then chapter 10 will also have like a standard in-class quiz and test. You should expect to see all the content from chapter 9 appearing on the chapter 10 quiz and test because the skills are kind of inseparable. So in chapter 9 we're like learning how to do derivatives, and in chapter 10 we're kind of like doing applications. So like you need the chapter 9 skills to do what you need to do. So they're inseparable in that way. Is everybody okay? Okay. So last time in class we talked about average rate of change, right? When I say average rate of change, you think slope, right? We talked about instantaneous rate of change, which would be the same as the slope of the line tangent to the curve at that point, which would be the same as the derivative of the curve at that point. So we can say those three things, and we use those terms interchangeably. They all are talking about doing the same thing. Or the answer to each one of those three questions is the same value. Maybe I should say it that way. So we've talked then about, okay, there's this concept of the derivative, calculating this instantaneous rate of change. We talked about formally how we do that by picking a point near the point that we're interested in and having it get progressively closer and closer to the point and look at the value of the slope and see if there's a pattern. We're essentially doing a limit there. And we came up with a limit definition then of the derivative. And we did one example of that and went, woof, that's enough of that. Is there an easier way to do this? And I introduced to you guys 4 rules for dealing with derivatives. So those 4 is the derivative operation distributes. You can pull a constant out front of the derivative operation. Derivative of constant is 0. And the last one was the power rule, where the derivative of x to the n is equal to n times x to the n minus 1. For what we're doing in this class, it's all you need, I think. I'll double check on that, but there's one other potential rule that I can't remember if they expect you to be able to do or not. It's the easiest one there is, because it's essentially nothing happens. But we'll cross that bridge when we come to it. So what we left off doing was some examples of just kind of taking the derivative of a function. So remember, there's kind of 2 different ways we can do a derivative. We can take the derivative of a function arbitrarily. The result is a new function where the values of x are the same as the values of x of the original, but the y values of our new function would give you the slope of the original function at that point. Right? So it's kind of like a slope function. So the x's are still x's, but the y's are the slopes from the original function at that point. Or we can take a derivative at a point, which is the exact same process, except at the very end, once we've calculated the formula for our derivative, we plug in the value for x. and get a number. Hi.
Can we do our thing right now? Because we're both in the studio.
I mean, I'm in the middle of stuff right now.
We like do it off to the side or like.
Yeah, I suppose.
Wow. Are you serious?
Mid-lesson? Are we in, what hour are you guys in?
Oh, second hour. Next time.
Yep. Okay. So let's do some more examples of this process because you've seen 2 examples so far. I'm guessing that's probably not sufficient to feel real comfortable yet doing this. Let's do a little bit more and then we'll kind of continue on here, yes? Okay.
I got 100 on this one and I did not fit it. I literally got the problems wrong when he was. I just wrote down everything.
Okay. So this is our next example. So when I look at this, the first thing I notice is I have addition and subtraction going on. That's correct. If I want the derivative, then I can distribute that derivative operation across my addition and subtraction. Everybody okay with my first step here? Okay. Now, I've turned this into taking one derivative into 3 simpler derivatives, right? Now, when I look at 2 of those derivatives, I have a problem. Which 2 are a problem? First derivative that I'm taking is a problem because what operation do I see in there? Well, you see that, but that's not the problem. The problem is the multiplication. If I look at this, the other problem is the second derivative. What operation in there is my problem? It's division. Right? The fraction means division. You, I should say, do not have a rule to deal with taking the derivative of a product or the derivative of a quotient. There is a rule. I'm not going to teach it to you. The IB doesn't expect you to use it. But I can't use the rules I have as they're currently put together, or I can't use the rules that I have to do the derivatives of these 2 parts as they're currently put together. So what am I going to do to get around this problem? I'm going to simplify this, each of these pieces algebraically. So the cube root of x to the 5th, I can rewrite that so that I have a rational exponent, right? The cube root of x to the 5th is the same thing as x to the what power? Oh, guys. x, the 5/3. Right, this is our rule from Algebra 2 and pre-calculus for the way to convert a radical expression into a fractional exponent. Do I expect you to have that remembered and memorized? Yes. This will be like the third time somebody's talked to you about this, and at one point this was a mastery topic in a previous course. So I do expect that to come back relatively quickly, and for us to, okay, I know I need to have this. I'm going to relearn it so I make sure I have it. How about the square root of x? How do I write that? X to the 1/2, right? There's a 1 as the exponent of the x that we don't write, and there's an index of 2 on the radical that we don't write. But we know we're there. Everybody so far so good? What about the division? How do I divide these? Guys. Right, our rule for exponents is if I have a quotient of two exponentials, I can subtract their exponents. Okay. So this should be the derivative of x to the 1 minus 3. Everybody feel okay there? Okay. So I've gotten rid of the multiplication or the division in the second piece, right? We're good there. Haven't gotten yet rid of the division in that first one though. We still need to do that. How do I multiply x to the 5/3 times x to the 1/2? Guys, wake up here. This is just like rules for exponents, right? We add the exponents. So 5/3 plus 1/2 should be 10/6 plus 3/6. So 13/6. Everybody happy? Okay. Again, if you need to write that out to make your common denominators, that's okay. If you can do it in your head, that's kind of a reasonable expectation at this level. At least as long as the fractions aren't terrible looking. It was like 57/39 plus 17/32 or 31st or something like, yes, okay. Like, I would need to write that out also, but like single digit denominators I would expect that we can probably handle in our head. You don't have to. Certainly you have a calculator on the quizzes and tests, you can use that. But like, you know, push yourself a little bit, right? All right. Now that we've gotten this down into a single expression of x, right? X is only in one place. There's no more multiplication, there's no more division anywhere going on in this. Now, I got it to a place where I can apply the final rules for derivatives to simplify, or to finish this problem off. So what is the derivative of x to the 13th sixth going to look like? The coefficient should be the same as the exponent. And then we subtract 1 from the exponent. Okay. I'll simplify that a little bit further, deal with the fractions. How about for the next piece, the derivative of x to the negative 2? The new coefficient should be negative 2, and the new exponent should be negative 2 minus 1. And what's the derivative of the constant 6? It is 0. Okay. My last little pieces of cleanup here. 3 over 6 minus 1, or 13 over 6 minus 1 is 13 over 6 minus 6 over 6. So that's 7 over 6. And then negative of a negative is positive. And negative 2 minus 1 is negative 3.
Do you have to put the plus 0 or no?
You do not need the plus 0. You can just drop it because you add 0 to anything, it doesn't do nothing.
Yeah.
So you can just, it's not wrong to put it there, but it's unnecessary. How was that? How did that feel?
I'm good at that.
What's the worst part? Doing the algebra in the beginning to get it to a point where you can use your derivative rules, right? The saying in calculus is, the calculus is the easy part, the algebra is the hard part. Right? That is fairly standard. Put a circle around these. If you don't have these at the tip of your fingers, like, make sure that you refamiliarize yourself with these because they will be useful. All right, let's do one more of these and then we'll kind of move on. Is this helpful? You feel like you're getting the hang of this? Enough talking through like what I'm thinking and what I'm looking at while I'm doing the problem to, because this is the first time any of us are doing this, so I want to make sure I'm being thorough here. Some of the other stuff that's like we've done this before, I can skate through a little bit. And I'm like, hey, just need enough to jog your memories. You guys should know this. This is new. Okay, so this is the function that we want to take the derivative of. All right. First thing I notice, I have an addition symbol, which means I can distribute the derivative operation to each term, right? Okay. Are either one of these two terms in a place where I can apply my derivative rules? No. Right? Why not? I have x's in multiple places, right? There's some division, some multiplication, all that stuff has to be resolved before I'm ready to apply my properties for derivative, or my rules for derivatives. Everybody good? Okay. So it's going to be algebra time for a little bit before we're able to do much with this. What am I going to do here? What should I start by doing? Notice the denominator of this fraction is a monomial. So I can rewrite this single fraction as the difference of two fractions that have the same common denominator. Everybody's okay with that? Now, at the same time, I'm going to rewrite the radical as a fractional exponent. What is the exponent on that? What should the exponent on that be? 3 over 2, right? Now, the second term is multiplication division. There's no addition subtraction there, so there's no need to make common denominators, right? Instead, what I'm going to do is rewrite everything with a fractional exponent. I guess there's some reducing of coefficients that I can do as well, right? So I have 2 times the square root of x times the 3 times the cube root of x divided by 6 times the 6th root of x. 2 times 3 is 6. So those can all reduce out of there, right? Everybody happy there?
Yeah.
Okay. And then I have that. Does everybody feel okay where we're at here? Okay. Let's continue simplifying. How should I reduce 7x squared over x to the 4th? Okay, so 7x to the 2 minus 4. Always top minus bottom, which is just 2 minus 4 is negative 2. Is it okay if I just...
Yeah.
Okay. Just checking. The next one is going to be 3 over 2 minus 4. So 3 over 2 minus 8 over 2, which will be negative 5 over 2.
Yeah.
And again, if you wanted to write that as 2.5, that would be fine, right? Negative 2.5 is fine. It's a terminating decimal, so there's no problem there. I'm going to raise a fraction because, I don't know, it's like the better, more proper way of doing it, but it's not wrong to leave it as a terminating decimal. On the next piece, let's multiply the top together first. What's to multiply the tops together? What do I need to do? Good. So 1/2 plus 1/3 is 3/6 plus 2/6. So that should be 5/6. It's hard to say. What's nice there, though, they're all sixths, right? So that'll make the reducing easier. All right. Let's continue. So I'm going to distribute the derivative operation through this one. Now that it's a subtraction problem, I notice I can distribute again. And at the same time, I'm going to pull the 7 out front. Now 5/6 minus 1/6 is 4/6, which also reduces to 2/3. Does everybody feel okay? Now everything is just like x to some power. I'm ready to do my derivatives. What's the derivative of x to the negative 2? The new coefficient should be -2, and then we have x to the -3rd. We just subtract 1 from the exponent now. Okay, how about the next one? The derivative of x to the -5/2. The new coefficient should be -5/2. And then the new exponent should be -5/2 minus 1, which is -5/2 minus 2/2, so -7/2. Or you could write that as 3.5, right? That's fine still. -3, you know what I meant when I said. Everybody still doing okay?
Yeah.
Okay. The last one, the derivative of x to the 2/3.
2/3.
2/3 minus 1 is 2/3 minus 3/3, -1/3.
Yeah.
And then my last step will be just cleaning up a little arithmetic here. So -14, and then plus and that's a good final answer. You okay here? Now these last couple that I gave you are harder than probably anything you would see on the AP or the IB exam that they would expect you to take the derivative of. But like if you can handle this, you can handle, if you dodge a wrench, you can dodge a ball.
Yeah.
Kind of philosophy here, right? How many of us in this room are in physics right now? I am in the wrong page here. Where am I? Up 3 more.
There was one else.
People in physics?
Huh?
Okay. So, in kinematics, the very beginning part of physics, there's 3 quantities that you'll talk about: position, velocity, and acceleration. These are all related to one another because velocity is the rate at which position changes. Acceleration is the rate at which velocity changes, which means that they are all related by the derivative. So the derivative of position is velocity. The derivative of velocity is acceleration, which means that acceleration is the second derivative of position because you take the derivative twice to go from position to acceleration. Everybody okay with this idea? This relationship that these quantities can be, I can retrieve velocity or acceleration if I'm given position, will be a key idea for most of these IB problems. We love this because it's overlapping with a different subject matter and gives IB all the feels, and we can make every class the same class, right? Like right now, math has just become physics, and we're like, yay, we did it! All right. So let's look at an example. says a ball is thrown upwards from the roof of a building. The vertical height of the ball from the ground, remember you started at the top of the building, in meters after t seconds is given by the function h of t equals negative 4.9 t squared plus 18t plus 50. The derivative of the function is negative 9.8 t plus 18. Let's just verify that for our own purposes. So normally, on all the previous examples, I had done ddx, but here, Mr. Kulik, you wrote ddt. Why did it change from x to t? No. Look at the function we're working with. What's the independent variable written as? T! So we're taking the derivative with respect to t. That's what the ddx is saying. Okay, so that just should match the variable in the problem. Is okay? Nothing special happening here. Doesn't mean anything different. You're just still doing the same thing. Just talking about t's instead of x's. So big whoop, right? Okay. We can distribute our derivative. We can pull our constants out front. We know the derivative of constant is 0. What's the derivative of t squared? The derivative of t squared. I'm just going to wait until somebody answers, because somebody should be able to answer this. Pat, what is it?
2t.
Thank you. He's not even in the class, guys. Come on. We've been doing this for 20 minutes or something. 32 minutes. It's okay, he's done this a bunch of times. Way more than you have. Don't feel bad. Alright. Everybody's okay? What's the derivative of t?
This is 2t.
So what's the exponent on t?
2.
No.
Oh.
On t.
Oh, no, nothing.
Nope.
1.
1.
Yeah.
So the exponent becomes the coefficient,
Okay.
and we subtract 1 from the exponent.
Yeah.
So I have 1t to the 0.
Okay.
What's t to the 0? Nope. Nope. What's anything other than 0 to the 0 power? Olivia? 1. So the derivative of t is going to be 1. And there is my derivative of position is equal to negative 9.8 t plus 18 as quoted in the problem, right? They told us this already. I'm just confirming it. Now this is the same as our velocity, right? Why do I know that that's the same as velocity? Because it's the derivative of position. Because I just took the derivative of position, I know my equation is a velocity equation now. So part A asks to find the initial velocity of the ball. What time is initial? What number of times should initial be? initial means in English? If I said to define the word initial.
First.
For the start, for the beginning, what value for t would indicate the start, for the beginning?
Zero.
0, right? There you go, yes. Right, I'm going to throw the ball up in the air. At the very start, how much time has elapsed? 0. So I just want the velocity at time 0. And then this is meters per second. Okay? Part B says, find the time at which the velocity of the ball is 0. Interpret the meaning of this. So I want to find when v of t is 0. Well, the equation for v of t is this, right? I'm going to subtract over the 18 and then divide by negative 9.8, right? Everybody okay with that? Now let's put on our physics hats and think about what's actually happening. So we're standing on top of a building. We throw the ball up into the air. Let me draw a picture. And the ball goes up and then down, right? What part of this path is where the ball has 0 velocity?
So the person is.
Nope.
It's at the top.
Yeah, right here, right? Why is that going to be 0 velocity? You throw something up into the air, and at that instant, when it reaches the highest spot, it's changing from moving forward to moving backward. The velocity there has to go get smaller and smaller and smaller, close to 0, and then turn negative, right?
Yeah.
So at some point there, when it changes direction, it's going to have 0 velocity. Okay? So it's a change in direction is kind of what that's indicating to us. Is everybody okay how looking at the picture helped inform that? Okay. Again, those of you that have been in physics have a little bit of an advantage here, just in terms of thinking about the problem. You guys, I'm sure, have done a bunch of velocity time graphs and stuff in that class to where, like, I got a handle on how position and velocity and acceleration all interact, and that's helpful. But not a prerequisite. Find the velocity of the ball at the moment it hits the ground. Okay, do we know what time? We need to know the time the ball hits the ground in order to compute the velocity when it hits the ground, correct?
Yeah.
Do we know what time it takes for the ball to hit the ground? Not yet, right? We're going to have to figure that out. Hits the ground, is that talking about a velocity or a position?
Position.
A position. What position is hitting the ground the same as? 0.
I don't think so.
So we're going to start by solving for the time by figuring out when h of t is equal to 0. Is everybody okay with that? Now, h of t is what type of an equation? As specifically as you can make it. What type of an equation is negative 4.9 t squared plus 18t plus 50? More specific than that. Q. U. A. Quadratic. How do we solve the quadratic equation? What are our methods that we could use? You could use the quadratic formula. You can factor. You can graph and look for the intersection. On your IB exam, where you have access to a calculator and time as a factor, which one is the quickest possible route? Graph it and look for the x-intercepts on our calculator, right? That's would be my recommendation to do. Now, could you do other things? Yes. Are they effective? Sure. Are they more time consuming?
Yeah.
Possibly. Right? Especially when the old IB here doesn't mind if you, or kind of expects you to round things to 3 significant figures. So there we go. Now I'm just going to graph this doing zoom standard and take a look. Which x-intercept am I looking for, or am I interested in? Because I see 2 of them. The one on the left or the one on the right? Why?
It's direction still.
Nope.
Either one moving down the up or trying to it down.
Nope.
Okay.
What is this value that I'm finding? It's a value for time. Time must be a positive number, right? Any negative values for time are insane answers. We don't give insane answers in this class. We're only looking for the positive results here. I keep coming with the trying though, Nicole. Don't be frustrated. Okay, you're doing fine. So I'm just going to use the intersect command. Oops, there we go. There we go. So 5.52. And I want the velocity, this is when the ball hits the ground. If I want the velocity when the ball hits the ground, I'm going to do V of 5.52. Now, what kind of number should I be expecting to get here? Should this number be negative or positive? Is the ball going up or going down when it hits the ground? Down. I should expect to get a negative number here, right? Let's just plug this into our calculator and confirm that. Yup. So negative 36.1 meters per second. How do we feel? It's okay? All right, so we did a lot today, right? We looked at everything. How to use our derivative rules to find the derivatives of things, right? We talked about the relationship between position, velocity, and acceleration, and how to use the derivative to relate those 3 things together, for the formulas for those 3 things together. We talked some more about the relationship between slope and the derivative. I think this is probably a good stopping point. So at this point, you guys, we've done enough for you guys to do the 9.1 and 9.2 homework. And I don't think that you need to use the derivative rules to do the 9.1 and 9.2 homework. It's going to be mostly like picking a value for H and getting closer and closer and just like plugging the values into a table and then looking at the slopes like we did in the last lesson. Or it'll be a problem like this where they give you the equation for position and velocity and ask you some questions. But it's okay to use, you know, the derivative rules. It's okay to do that. I gave them to you early. I just think that the book just organizes things in kind of a strange manner that doesn't feel very sensible to me. So I've gone a little out of sequence here. I think 9.4 is when they're supposed to give you these rules. I gave them to you early because it felt to be a appropriate time. I'd rather do the rules first and the application second. They like to do applications and then kind of like fill in the rule here. And it's like, why did we do all these applications before we had the rule? Really? To make my life easier? I don't know. But that feels good for us for today. We still have 15 minutes or so, but I'm gonna stop here. Any questions about what we've done so far? So again, this is new for every single one of you. If you are not in the regular habit of completing the homework in a fashion other than copying the answers out of the back of the book, I highly recommend you spend some time engaging with these assignments because the practice is really beneficial. What we're doing here is not difficult, but it does require practice to get accustomed to it. Most of these things that we're doing, once you get comfortable, are things you can do in your head. Doesn't require much writing down, but you do need to spend some time like getting comfortable and getting good at it. And you can't do that just by watching things. You have to do it yourself. Okay? So again, if you haven't been in the habit of completing the homework without copying the answers out of the back of the book, I strongly suggest in these 3 chapters that you spend some time really engaging and doing the homework yourself. Like for sure, check your answers, that's fine. Totally do that. If you get it wrong, try it again. Use the back of the book, the answers in the back of the book in a way to help mold your understanding rather than just like, I just need to get this done to get some points. Right? If I could get you to do the homework in any other way other than assigning points for it, I would. Just like go do homework and I don't care if it's right or wrong or when it gets done, but like doing it for you so that you know how to do this, but I don't think anybody would. At least the past tells me this. Okay? Questions? The 9.1 and 9.2 homeworks won't be due Sunday, it'll be due the following Sunday, right? Because the B period hasn't been assigned them yet, so there's no sense in having them 2 different classes doing 2 different days, that's silly. Okay, that's all I have. Yay, we did it!